Hello, everyone. I'm really happy that so many people are interested in mutation testing. I came here from Poland, and I work at Google. And do you know why NASA spacecraft crashed in 1999 while traveling to Mars? And it is somehow related to the fact that even though mutation testing was discovered in 1971, it was not really used until 2010. And all this we will cover, and also the idea of mutation testing, as well as the implementation on this presentation. Let's start with a scenario. Imagine two engineers discussing. I wrote code for a spacecraft. How do you know that it works? So what is the answer of the engineer? It's like, I just know. It's probably the most common answer. It's just too easy to test. Or I feel it. It's like, and that is what could have happened in NASA in 1999. They didn't test their code. So there was a bug in the code. In 1998, they created this wonderful device. It was a kind of device to measure things on Mars, and they sent it into Earth. It was called Climate Orbiter, and it weighed half of a ton, so kind of a car, like a car. And to go from Earth to Mars, it takes half a year. And everything was fine. This device was traveling to Mars happily. There was a contact with the ground computer and with the base. And all of a sudden, the contact was lost. What happened? So there was a bug in the code. And it's the most famous bug ever made by a software engineer. The spacecraft calculated everything in a metric system. However, the ground computer calculated everything in pounds, like in the US. And there was no conversion in between. So in the result, the speed of the aircraft was too high while going into atmosphere of Mars, and it burned. And okay, just you might say shit happens, and it's like there was no people on board, so luckily no one died. But guess what? Devices like this, they cost a lot of money. This one costed more than $300 million. It's still just money, but if you think about it, it's like you would need 234 persons in America working all their lives to provide this money. In case of Poland, it's even worse. You need 700 persons. But I don't know how does Romania plays. Even worse. So maybe, yeah. 2 screens, like we would need a separate screen. And that's all because of the bug of one engineer, like. So how this conversation should look like? I wrote the code for the spacecraft. How do you know that it works? I wrote unit tests. But how do you know that your tests work? But really, I mean, I write code, and I test to test my code. Then what? Then I should write the test to test the test of my code? And then what? Test to test the test of my code? And then write the test to test the test of my code? No, it's like, it just doesn't make sense. So we need something better. And so does testing make any sense at all? Like, if you think about it. If you don't know if your tests are fine, so what is it for? So luckily, there is a method to test your test without writing more tests. Think of a code like this. Just the simplest code possible. A plus B, we just sum two numbers. So if we write a test for them, how do we usually test if the test is fine? We run the test coverage. But, like, there is a problem in test coverage. According to common sense, or a guru of the common sense in the IT world, Uncle Bob, he said coverage does not prove that you have tested every line. All it proves is that you have executed every line. And that is a big difference. Because if you think about our little oversimplified example, we can have code like this, just summing two numbers, and it can be perfectly covered with a test without any assertions. Because like someone wrote the code just to fulfill some requirements about the code coverage level. So we need something better. We still need something better than just code coverage. And luckily, the something better came in 1971. There was a guy called Richard Limpton, and he found a good answer. He wrote a paper about it. So he asked a more fundamental question. What is the testing for? Like, how would NASA be better if they tested their spacecraft? And he concluded that we write tests to find bugs. If we imagine like a perfect world without bugs, then there is no need for testing anything. So he thought, so tests are good if they find bugs. So we could create artificial bugs, and see if our test finds them. And he wrote in his paper, like, if you want to know if a test suite has properly checked some code, introduce a bug. We think about an example. How could we introduce a bug here? So just as a plus b. We could just simply change a minus b. That is definitely a bug because we wanted to have a sum, but we subtract the values. And actually, that's mutation testing. We just change the code and run tests over the code. If the test fails, our tests are good. So you may ask, like, is the whole idea behind mutation testing? And actually, yes, that's the whole idea. So we could end up here. But let's go a little bit deeper. But before we do that, let's clarify the terminology. So this artificial bug is called a mutation operation. Code with artificial bug, so this change code, is a mutant. When the test fails on the mutant, we call it that it killed the mutant. However, if the test succeeded, even though the code is mutated, we say that the mutant survived. So in our example, like this a minus b, changing this from plus to minus is a mutation operation. This return a minus b is a mutant. If the test fails on that, we killed the mutant. If the test succeeded on that, the mutant survived. So just remember, killing is good in this context. If we kill all the mutants, it's better, it's good. You may say, like, okay, but my code is much more complex than adding two numbers. This sounds good, but that's why we have a lot of different mutations. We have like, and just to quickly see what can we mutate is just what we've seen, like math operations from plus to minus or multiplying to division. We can also do some boundaries, like tighten them or make them wider. So like instead of greater than, we have greater or equals than. We can have some negation, so we revert the condition. Or some complex stuff, removing if statements, removing some method calls, or modify the return to always return null, for example, or a default value for primitives. We can, the same way we can modify some constants. You can probably think about of more. So how does it work? We have our code base. And to each place where it is possible to apply any of these mutation operations, each such case create a new mutant. So we can imagine, like, if we look through all our data or our code base, then we create a lot of mutants, really a lot of them. And then against all these mutants, we run our unit tests. If on particular mutant, at least one of the tests fails, then we kill the mutant. However, if there is a mutant on which all our tests passed, it's like, then we have like a black sheep. Yes, we have a problem here. We have a test flow. But do I need to change the code on my own? And obviously nobody would do it because it would be like a lot of work just changing all the operations. So luckily there are frameworks for that. And what I will advertise here is a PID mutation testing framework, which is dedicated, which is now mainstream for Java. For other languages, there are other frameworks. What is cool about this framework? I mean, one cool thing is that it has a great logo, as you can see. I have my personal list of the best logos of the software, and it's on second place. Obviously, the first place is taken by Docker. No one has better logo than Docker in IT. So this tool you can just apply as a plugin to your IntelliJ, or as a command in a command line, running from command line, or you can add it as a Maven plugin or Gradle plugin or whatever you like. Since I love IntelliJ, I will show how to do it. I will first show how to do it with IntelliJ. So if you would like to use it in IntelliJ, then it's very easy. All you have to do before using that is just to install the PID runner plugin. And you probably know how to do it, but just to be from the beginning to the end. So to do it, you click on the settings, click on the plugins, and it's in the official repository of plugins. Luckily, we don't have to do a lot just to find the PID testing. Install this, and we are all set up to start using that from IntelliJ. So coming back to our example, we have our code, we have our test, which does not test anything, but the code coverage is still 100. So how can we apply this PID testing framework? So we can open this class. It's exactly what I've shown on the slide. And the test is also that stupid. And we can even run this test to see that it really works. You can even run the test coverage to see that it really provides the 100% coverage. It's small, but if you look here, it's perfect test. So how to do it? And even we can see, like IntelliJ shows here what lines are covered and it's covered. Okay, how to do it with PID testing framework? So we can just edit configuration and just add a configuration for PID runner. We can even like leave the default configuration or just name it better. Basically, it's all we have to do is just run it. We can also configure some other things here, like where should be the code taken from, where the report should go in. Then if we click OK, then we can start it. So it prints a lot of things of console as everything. Here we can see that it created in fact two mutations. One is the math mutator and the other is return values mutator. Let's have a look at this first, like math mutator. This is exactly what we've seen on the slide. So it changed plus to minus. Here we see that it was generated, but it was not killed, so it survived. Here maybe is also a good time to see like what could be other results of acting like, because killed, survived, it's clear. However, like PID operates on the Java bytecode. It changes things in Java bytecode, and it's like some code can be not executable anymore after the changes, and that it will end up here in non-viable. Timeout, because you can imagine if it changes some operators, we can end up in an infinite loop. So we need some timeout, because otherwise we would never finish the test. Also, the memory can be exceeded and some other like runtime errors. So let's try to fix this test. Write a perfect unit test for that. Even perfect like in the terms that we have given, when, and then. Only one assertion. It's really perfect. Okay, we just add two values and see if it's free. So let's see how would it work with the, I mean, if we run it, we would get almost the same report, just see that the mutant was killed. But okay, do I need to read the console? I mean, it's 21st century. Just, come on, it's like, and no, we can run it and see the report is generated in HTML. So we have our test fixed to the correct test. We can run it again. If you have a good side, you would see that, okay, the mutant was killed. And at the bottom, we have the report generated for our test run. Here is a very simple example. So we have 100% of coverage in terms of mutation testing. You can open each package and each class and see the line coverage in terms of mutation testing. So what is interesting, like every line has like a number here, and it's how many mutants were created, and we can even like look at what mutants were created. So the one you already know, it changes plus to minus. Another one is a mutant that just returns 0 or 1 in case of the, so if the result was 0, it will return 1, and if the result was something else, it will return 0. So like this, we can like analyze our code. And you may think now that it's cool what I presented, but when I first seen that, I thought it's a very good idea, but it will never apply to the whole code base, because it looks fine as an example, like summing two values. Then when you can trace everything, it just looks cool and great. But what about bigger projects? And the best thing is to just try. Before thinking, just try. What about bigger projects? And I tried it on Google Guava, which is like the best library for for Java. So you can just, and it's open source, so we can try it here. I try it, but I will not show it here because, you know, I work for Google, it's from Google. I will not torture the library from Google here in front of all of you. That is why I took the competitor, which is Apache Commons. And we will have a look at Apache Commons. And I've selected only one library, CSV, which is very small, still not to take you, you know, not to let you wait like looking at the console for half an hour, just a small library, which is very small, like 4,000 lines of code. However, it's very widely used. I mean, if you did something with CSV, it's highly probable that you used this library. So let's see how the mutation testing will apply to the library. So if we, okay. So we can just clone the repository from GitHub. It's available. So you don't see the beginning of the console, but okay, it will be fine. So basically, what I did, I cloned the repository to my nothing fancy, just git clone. Then you can open this. The project is run on Maven, so everything we have to do is just open the POM XML and add the Pit plugin there. This will be the only change we will do in the code. How to edit? Just find the plugin and open the official Pit homepage and just paste it there. This is the only change we did in the code, so just save the file, we exit. And we can run everything from Maven. To run it, we also copy paste. It's just this technique of coding when you just copy. You probably know it, yes? There's like Stack Overflow oriented programming. But okay, now serious stuff. Okay, so what we did, we just ran the Maven test just to first compile the test, and then run this copied thing from Pit framework, and it's compiling the test, running the test, and generating the reports. So I didn't speed it up, so just you can really feel how much time does it take. What is interesting here, like it's not so slow because even though we create a lot of mutants, we operate on a bytecode, so we don't need to compile it again, code, which is cool. Also, like it's run in parallel, which is also a kind of feature, not maybe, you can already see that we can run tests in parallel to kill the mutants, so it's nothing fancy, but still an improvement. Also, what Pete does, it organized in the tests, it's like sort the tests from the test that is the fastest to the slowest. So, because if the mutant is killed by one test, there is no reason to run other tests on the same mutant because it's already killed. The main problem, in fact, what you see here, it's timeout. Because for each timeout test, we have to wait something. And it's like, in this example, that's the main reason why it takes so long. If we didn't have timeout, it would be way faster. So you see, like you can use it, but it's still not so fast. You know, like if you would like to run it over your code base, which is probably larger than 10 classes, it may take some time. However, usually you run it over one class that the test you are actually writing at the moment. To see, like a lot of mutation ended up in a timeout. Come on, you can do it faster. Come on. Okay, so it took 2 minutes 20 seconds in total. So now we can open the reports. You also don't see it because it's somewhere there on the console, but I just do nothing fancy, just open the reports in the browser, and you will see it browser in a second. So it's just generated by dates, and there is a nice index HTML, and okay. So what we can see in this library, it's pretty well covered, but however, it's still like far from 100%. We can see all the classes here and coverage by a class. So I would say it's not bad, but could be better. Let's open like what things are not tested right. Well, let's see. It's all green, all green. Yeah, it's all green, but okay. The first thing that didn't test right is the flash method. They either didn't test it at all, just probable, or they did it not correctly. So they have some bug in the test, or they just don't have the test. So for each line, like this if was removed, but still everything passed. And also this was not called at all. You could go even farther and see what happens. Okay, print line doesn't matter. But okay, this looks interesting, because like if the character is CR, so kind of end line on the MacBook, I think, then this is not well tested at all. So it created like 5 mutants and all of them survived. So this case is for sure not tested. So how can they know that it works? That's the question. Maybe they just know it, but you cannot be sure. Like, so we already found like 2 things that are not tested. We don't know if there is a bug inside or they are not tested, but we for sure know that Apache didn't test 2 parts of their code. So coming back to our story, like about NASA engineers, so why they didn't use it like in 1998, even though like it was created in 1971? So the story of mutation testing, okay, it was created in 1971. But first, you know, when someone writes a paper, then it's used in the academics, somewhere on the universities, some guys are writing. Or normally it takes some time to go into the industry. So the first Java framework was called Jester. It has pretty ugly logo, as you can see, like it's one of the worst. Like if I kept the list of the worst logo of IT, that would be somewhere there. And Pit was created in 2012. So you see like a gap of 40 years, not using that, even though it's so cool that I just showed you that it's cool. So why is it so? And it happened that there are two reasons. There are two good reasons why it wasn't used for so much time in the industry. And the first reason is the equivalent mutants. Think about a code like this. So if A is greater or equals than 100, we throw an exception. If it's smaller, then we execute some function. So if you create a mutant, which just removes if, the code is still the same. Like the semantic of this mutated code is exactly the same as the semantic of the production code. And that's the problem, because we will never kill a mutant like this. Because again, the mutant is exactly the same as the production code. Here we could say, okay, but even though it's not a bug, it's an not clean code, because this could be removed. However, you can find cases where it's not about cleanness of the code, but it's like, there is still like the mutant is still the same as the production code. And it happens that it's not so easy to check it. It's just not easy. Looking at the code in the mutant, it's not easy to decide if it's the same or not. What is worse, even the Pit mutation testing framework doesn't solve this problem. So it might happen that we have a red line, we have red coverage, but in fact, it's just that the equivalent mutant was created. What Pit framework did and improved was that it just created like so-called mutators, which created mutation, and just grouped them in a different way. Like, for example, it said that changing plus to minus will almost never cause equivalent mutant, and just group them. And these mutators, which are highly probable to result in the equivalent mutant, are not active by default. So just reduce the probability of having like false code coverage. And the second reason was slow performance. You may already seen, like on the small library, it took some time, but if you used like this ugly gesture, it would take much longer, way longer. So you probably see why it's slow. We have a lot of mutants, and we have a lot of tests. And if we test all the combinations, it just takes a lot of time. So what Pit mutation did, and it was quite smart, then if we have like this code like this, our favorite part of the code, before even creating the mutants, we run all the tests, check the coverage, like normal coverage, not mutation coverage, and see which test caused this coverage. So in our case, it would be probably just one test touching this code at all. All the other tests will have nothing to do with that code. So then we create a mutant, obviously only this, if we create like these two mutants, we created like plus to minus and return 0. All other tests will not kill these mutants. So we just need to apply only this one test. So before running the mutants, it groups the tests for, like maps the test to mutants. And there's also a nice improvement. That's why now you can use it in industry. And you may say it's cool, as before, but I can run it from IntelliJ. I can even install the plugin. But what about my team? They will never do it. They are lazy, and I will not force them to install some plugin to IntelliJ or convince them. So what about them? And let me tell you a story here. Like 3 years ago, I worked for the banking industry. And as you can imagine, it's still a lot of money. Like NASA, a lot of money. Banking industry is even more money. That is why we had like we really had to focus on the code quality, because bugs were very expensive. But we had quite a lot of time for writing the code. There was no big pressure. And our team was distributed. So we had one team in US, in Stanford. We had one team in Krakow, where I worked. And we had one team in India, in Hyderabad. And the code was very well separated into, it was a modular application. So we didn't, in fact, didn't touch the other teams so much. We just developed the code in our modules. And everything went fine. We had, in our continuous integration, we had a threshold on 100% code coverage. So if you had less, you just couldn't push the code to the GitHub repository. And everything was fine until the moment when I had to create a new module. Because the construction of the module was so that there was a main class in the module which created all other objects from the module and injected them. You can think of this like a Spring configuration, or if you use Juice, it's like the Juice modules. So just one class has to create this object somehow. And I thought, how to test this class? Because this is what I call like main class paradox. Because like it just cannot test the main class, because if all the responsibility of the main class or this configuration class is to create other objects and inject them, it doesn't make sense to test it, because it just does nothing. There's one reason, and the other is if you tested the main class, you would test the whole system. So it would no longer be an unit test, but an integration test, unless you use some, power mocks or some ugly stuff, reflection. And so what I did, so I thought, what do you do when you have to write something new? Just go to Stack Overflow. But if it was our local problem, so what I did, I started to read the code from others. And I started to read the code from this guy from Hyderabad in India. And just was reading code. Finally, I found the test. And when I found the test, it was like, okay, it was well structured. It was given, when, but there was no assertions. And the problem is, it was not only for this main class. It was an older test that didn't put assertions, because they just wanted to skip this threshold on the continuous integration, but they just didn't care about testing. And I don't know, what to do with people who write tests without assertion. Because I don't know, should you laugh on them or just, I don't get angry. So we can do better with mutation testing here. We can apply our coverage report to our continuous integration, for example, Jenkins or any other. The small problem is that we have this equivalent mutant, so it would be hard to set this threshold of 100%, because there may be a line that is not well covered in terms of mutation testing, but it's still fine. So what I recommend is just adding the generation of the report. So it has to be checked by human, the report. But at least you could see, if in my case, it would be 0% of the coverage for all their modules. So it's it just tells you something. So it is something I really recommend. Put it into your Jenkins or other CI, creating the report. Okay, so, but I'm telling a lot, but what do people really use mutation testing, or is it just still like an experiment? And yes, people do use it. And CERN announced that while building the LHC, Large Hadron Collider, they used mutation testing. They didn't use Pit framework because they wrote it in Python. So they used a library for Python. Also, the Norway, for the voting system, they announced that they used mutation testing while implementing their voting system for their elections. But actually, I think in most companies, now it's IT companies, there is mutation testing. For this banking industry, we introduced it into the process because it's just simple and you can do it quickly. So just test your tests, because it's it gives you the guarantee of that your tests are fine. Then you can refactor your test, or you can do all nice stuff. And do it because you can, crash something, or you can lose a lot of money, or have a shame over the word, or just laughter or anger. It's so just test your tests. Thank you.